All right, thank you. Thank you, Ken, for that nice introduction, and thank you to the organizers for inviting me. It's always great to get back to IPMU. I did have a wonderful time here as a postdoc, and I always tell people to come and visit as often as they can. I'm going to be talking about extraordinary supernova today. There's a few supernova experts in this room. There's a few more that are not supernova experts, I believe. So I'm going to start by talking about normal supernova, just to give you some context. So there are different flavors of supernova. That's kind of the bottom line here. There are the events you may know about, these so-called type 1a events, which are now shown to be thermonuclear explosions involving white dwarf stars. White dwarfs, of course, are very stable objects by themselves, so you need a companion to add mass to that system. And then there's a completely different category of supernova, usually called core collapse supernova. And these are the explosions of very massive stars, so stars that start their lives off with about 8 times or more than the mass of the sun. And these get to the end of their lives and create heavier and heavier elements in their cores, build up these dense cores, and then essentially under their own weight collapse and rebound into a supernova explosion. If they do that with this shell of hydrogen intact, we will see hydrogen in the spectrum. We'll call them type 2. If that hydrogen has been blown off or stripped off somehow, we'll call it a type 1 of some variety. If we see helium, we'll type 1b. If we don't see helium, we'll call them type 1c. Type 1c is the default class. Everything goes in there. All right. So we do have these different types of type 1a supernova. You probably do know these type 1As a little bit better because these are the ones that they hand out Nobel Prizes for. So these type 1A supernova have this nice property that they have very similar peak luminosities. And if you correct for the fact that the brighter ones actually have a bit of a broader light curve, they take a little bit longer to rise and fall than the fainter ones, you can actually come up with a very standard object whose brightness you know. And if you know the brightness of an object and the intrinsic luminosity, I should say, of an object, and you see how bright it appears to you, you can of course use basic inverse square law and you can figure out the distance. So these have been used to measure our universe, and as this work was awarded the Nobel Prize in 2011, which was right after I actually got here at IPMU. It's just a few months into my term here. I had actually worked with Saul Perlmutter. This is the work I did as an undergraduate before I even got to Texas and started my supernova search. So I was lucky enough that I actually got to go to the ceremony, as some of you know. So it's a wonderful, it's a fun time. You should all go. All right, so these type 1a supernova, this is a light curve now I'm plotting. So this is time in days, and this is brightness. And supernova, basically, they get brighter and then they fade away. That's what supernova do. They're very bright. The peak luminosities here are about 6 billion times the luminosity of our sun. So incredibly bright objects. That's why they're so useful as standard candles, because you can see them so far away. Now, as we heard in the introduction, I discovered actually a new class of objects that are now called superluminous supernova as a graduate student. And these, I'll just show you one here, are significantly brighter. This is a log scale here. So we're seeing now not 6 times, but more like 60 times, 60 billion times, sorry, the luminosity of the sun here. And the amazing thing about these is that the energy budget is just incredible. So they're putting out more energy than a type 1a supernova for 5 months, right? And this has been a great puzzle to explain. How do you get something that produces that much energy and dumps it out? It's still something that people are working on. So this is the light curves. The key things I want you to take away from this is that a normal type 1a supernova kind of rises in 2 to 3 weeks, reaches its peak and then fades away over about a month time scale. Whereas these superluminous supernova, this is just a representative example here, they tend to rise over month periods, maybe 2 months, to rise to peak and then fade away. Those are the light curves. We can also take a look at their spectra. So these are now spectra of different types of supernova. This is rest wavelength in angstroms across here, so your UV light over here and near-infrared over here. I'm showing luminosity density here, just to give you a relative sense of how bright these supernovae are, how luminous they are at different wavelengths. Here's your classic type 1a supernova and your type 2 supernova. Spectra convey a huge wealth of information. You can look at this and you can say, okay, there's that hydrogen. So that's why I know this is the type 2. You can look and see this one doesn't have hydrogen, but it has a silicon there. And let me just take a moment and let you appreciate that these supernovae are releasing lots of the elements that we care about very much into the universe. So it's not just, we can look at these as probes. Type 1a supernovae are great probes of our universe, but they're much more practical if you care about things like life on Earth. If you care about, say, oxygen, there's an oxygen line there. That wasn't forged in the Big Bang. It was made in supernova. This is where the air you're breathing came from, supernova. Some of the air. Calcium in your bones came from supernova. The iron in your blood, it came from supernova. So these are very fundamental objects to us as living beings. But what I want to show on this slide is that if you look at these luminosities as a functional wavelength here, luminosity densities, you can see that type 1a supernova and type 2 supernova kind of reach a peak around 4,000 angstroms, and then they fade away as you go off into the bluer wavelengths. Whereas these superluminous supernova keep rising and rising and rising up to past 3,000 angstroms, maybe almost to 2,000 angstroms, where the peak of their SCDs are. And what this means is that you can detect these at very high redshifts. So these are potentially very interesting probes of the high redshift universe. If you're studying type 1a supernova, it gets very hard to find these things at higher and higher redshifts, because once you get past a certain point, your bandpass that you're using to survey starts redshifting farther and farther to the left on this plot here, and the flux of your type 1a drops out. So above around redshift 2, for example, it gets really hard to find type 1a supernova. Whereas for superluminous supernova, you can find these up to redshift 4, 5, maybe even 6 right now with Subaru. All right. So one of the key differences here is it appears that superluminous supernova stay hot for much longer time. All these spectra represent maximum light spectra of supernova. So why is it that these objects are so much hotter than these type 1a supernova? Well, the way supernova works is that you start off with a compact source. A lot of energy is released suddenly. The source expands, and as it expands, it cools adiabatically. So the temperature drops. If you want to continue to see that supernova over some period of time, you need to add energy to it. Otherwise, it would just fade away kind of like the Big Bang. It would just fade away. So all the classic supernova models have methods of adding energy from radioactive products that keep adding energy over time. For these superluminous supernova, we can't use these standard models. They just simply don't work. So we need a new power source, a new way to explain these supernovae. There's been a few models that have been proposed to explain the superluminous supernova. There's the three most popular, starting up at the top here, is the pair instability supernova model. This is not a new model. This goes back to the 60s. It was originally proposed to explain the deaths of the first stars in our universe, the very, very massive stars that formed in the early universe. Wasn't thought to apply locally, but when we started to find these high luminosity supernovas, this model was resurrected. Essentially what happens here is if you have a really massive star, the core is actually not supported by gas pressure. It's actually photon pressure that's supporting it. So you have an adiabatic index for this gas, which is close to gamma to the 4/3. And when the energies get high enough, the photons actually start pair producing. So you start taking those photons which are supporting the star and turning them into particles where they can't support the star anymore. And so what this means is if you look at some little fluid element, if you add just a little bit of energy to that fluid element, it can't, you weaken the equation of state. So if you add that energy, that fluid element can't expand enough to cool down. So it stays hot, and that causes more nuclear reactions to take place and more energy to get dumped in there, and then more and more and more. And what you get is a thermonuclear runaway. So these pair instability supernovae are actually taking a core of a star, which may be maybe 50 solar masses, a huge star, and you're burning that completely. So this is one way that you can make a tremendous amount of radioactive products, like nickel-56. And if you make a lot of radioactive products, then as the supernova expands, you have this heating built into it, so it stays hot for a long time, and you end up with something that has a large radius and still a high temperature. That's going to give you a luminous source. The next idea is circumstellar interaction. In this case, before you have a supernova, you have maybe a wind that's being cast off of the star. And then when the supernova explodes, you get this ejecta, which is moving at 10, 15, 20,000 kilometers per second. And so that fast-moving ejecta runs through this slow-moving wind that was cast off before, and you get an interaction. And that interaction will set up some shocks, and you can get energy from these shocks, which energizes your ejecta. And so effectively, as this shock wave moves out, as this material moves out, you get this large radius that stays hot, and that's why it looks bright. You're hot and you have a large radius. And then the third idea is this magnetar model. So in this case, when a supernova has a core collapse, you're going to form some compact object. It could be a black hole, it could be a neutron star. If it is a neutron star, you might expect its initial spin period to be very high, because you've conserved your angular momentum, and you expect the magnetic fields to be very high. If you have both of those things, you get a magnetar, and as that magnetar interacts with this, the plasma around it, it's going to slow down. It's going to spin down. And that spin down luminosity, if you can dump that into your ejecta, then again, you have a way to power a superluminous supernova. You're adding energy over longer time scales to keep that ejecta hot as it expands. Okay? Oh, and by the way, if you ever want to get a shout out from a director of a Kavli Institute, study what they study. So. All right. So what I got here in 2011, there was a tiny sample of these superluminous supernovae known. This is most of the ones that were actually known at that time. You can see these are the images of the supernova here. These are the before images where you just see the host galaxies or don't, because these are really high luminosity objects. They're actually much more luminous than their host galaxies. Entire galaxies of stars are pale in comparison to these events. So there's just a few known, but we're starting to get some sense of different groups. There's some of these supernova that have hydrogen in them, some of them that don't, so we have this kind of standard dichotomy. Things are starting to fall into place, and then this paper came out in 2013, so this is this discovery. We've already heard a little bit about this, but I'm going to give you my take on it as well, because it's a fun story. This is a discovery of Pan-STARRS 10AFX by this group of researchers here, predominantly at the Harvard-Smithsonian Center for Astrophysics. Very, very good people, very smart people. This is a great paper. I really enjoyed reading it. But it's a very puzzling paper because this is what they found. They found a supernova. Here's the light curve for it, that rose up in about 2 weeks and then faded away. And then they got spectra of that supernova. So nothing out of the ordinary here. That spectra of that supernova, and they found these narrow lines here so they could figure out what the redshift was. And they found a redshift of almost 1.4, which is very high. We weren't expecting that. And if you take that redshift and figure out the distance and then take the observed brightness of this, you can project a peak luminosity of 4 times 10 to the 44 ergs per second, which is a large number. That's a large luminosity. This would have been the most luminous supernova ever found. But it's not, as you may have already heard. This is very puzzling because it didn't fit in with this picture of the superluminous supernova, other than that apparent luminosity. It's not hot. If you look at the spectra, it turns over at 4,000 angstrom, just like the normal supernova do. It's not. It doesn't seem to be big because it's evolving on a rather fast time scale. You'd think if it was a very large object that it would take longer for this light curve to evolve. So we have neither one of these conditions that we really need to have a high luminosity object. You want luminosity goes as temperature to the fourth power radius squared. So you want those two things to be big, the temperature and the radius. Neither one of those is the case. They're both pretty normal sized. It's a normal sized object and normal temperature. So there didn't seem to be any way that you could make this a high luminosity object. And we did puzzle over this at the tea time. This is a picture from when I was at IPMU. That's actually me there sitting next to Ken, I believe, discussing maybe this paper. And we did this for a couple of days. I remember Ken actually coming out and putting the paper down on the table and saying, okay, explain this. Like, what is going on here? And we couldn't figure it out because it didn't make sense. And it shouldn't have made sense because there was something that was not right about this. And it took a while to figure out what this was. Eventually, I had the idea that since it looks so much like a normal supernova, why don't we compare it to a normal supernova? And so I did. The red is the data of their spectra from the Pan-STARRS event. The black line is a normal type 1a supernova, and they're actually excellent agreement. You may not believe this because it seems like there's a lot of noise here, but this is what people will actually work with when they do cosmology. The black line here, that's a high redshift supernova at the same redshift. The red is that template. And if you believe this match, and people do, this is classified as a 1A with high confidence. This is the gold sample of Riesel. Hopefully you'd believe this as well. So it's a type 1A supernova. And how do you get a type 1A supernova that luminous? Well, you don't. Type 1A supernova don't do that. We know what type 1A supernova do. We know that they have standard luminosities. And we can predict how bright it should be. And it's much, much too bright. So what happened? There's only one thing that could happen. Something along the line of sight made it brighter. So this is where we concluded this was a lensed event. Concluded the only way you could get this is that if somewhere along the line of sight between us and the supernova, there was some other body, and that body was acting as a gravitational lens. Right? This was a really exciting discovery, and it was a lot of fun to put this all together. I'm not going to tell you the full details because you've already heard a little bit about it from Hitoshi and from Ken. But I will just highlight again that, yes, all of us were actually at the same institute, Kavli Institute for Physics and Mathematics of the Universe. 11 people on that paper. There's no superscripts because we didn't need it. And it was just an actual pleasure working with everybody, all the people on this team. It was so much fun to come up with this idea and to see it through and to talk to all the people in the group. And everyone contributed and was fun to work with. It was just by far the best experience for making a paper I've had. So I really enjoyed doing that. One thing that was always a little bit unfortunate about this is that the discovery was announced, not our discovery, but the original discovery was announced years after the supernova had faded away. So we never got the chance to go back and look and see, is it actually lens? We concluded that there should have been 4 images of the supernova there, right? And we wanted to see that, but we couldn't. Fortunately, the universe does provide more examples of this, and last year, there was a discovery by the Intermediate Palomar Transient Factory, IPTF, of another gravitational lens type 1a supernova. This time, we caught it while it was in the act of exploding, and we managed to get high-resolution images. There's a discovery image, but then we got AO images from the ground and from space with the Hubble Space Telescope. And we actually could see the 1, 2, 3, 4 separate images in that kind of Einstein cross configuration for the supernova. So again, Kavli IPMU was part of IPTF, and this was an exciting discovery that we had coming out of that work. This was important for me too. You always have in the back of your head, like, I think I got it right, but is it really possible to have that? And when you actually get to see the lens resolve like this, whoa, that was exciting. It's great it gives you some faith that you're doing something right. All right, so IPTF found this one very interesting supernova. It also found a whole lot of other supernova, including those superluminous supernova that I've been very interested in. So we now have a sample now of actually a couple dozen events from Palomar Transient Factory, and have gone through now and started realizing that they're not all exactly the same. So even if we just look at the hydrogen poor ones, the type 1s, it seems like that group actually can be divided maybe into 2 different groups. So I'm showing that here with these 2 different samples. These are just taking a whole bunch of events at similar phases and showing them all together, the spectra together. And you're taking the averages shown in black here for each one of these samples. So these are all type 1 superluminous supernova, but some of them have these fairly broad features, and some of them have much more narrow features. So it could be that we have some kind of dichotomy within the type 1 class. Maybe this is a viewing angle effect, or maybe this is showing us that there are different progenitors. There's different ways you can make superluminous supernova according to the theorists thus far, so maybe everyone's right. Maybe the universe is very clever and does it in more than one way. So that's what we have been doing and what we are doing now. I also want to tell you a little bit about what we're going to be doing. So we have this great sample, but there's still these questions. We still haven't quite decided, are these magnetar-powered events? Are they circumstellar interaction-powered events? So we want another way to discriminate this, a better way to discriminate these. And one of the keys, I think, to doing this is actually getting early detections of these superluminous supernova. So it turns out that if you look at these events at the earliest phases, soon after they explode, they seem to always show this little bump here. So there's a bump, and then they go up to the maximum. Usually we only discover them somewhere around here, when they're the brightest. They're the easiest to find. But if we could start finding them here, and know that we found them there so that we can get a spectrum. So this first spectrum was taken here, months after the supernova actually exploded. If we can start getting spectra here, we can maybe distinguish between these different models. So I'd like to do that, but that's not easy. If it was easy, it would have been done already. The problem is these are very rare events. You only get one of these in a volume. You only get one of these for maybe every 1,000 or 10,000 regular supernova. Now, they're very high luminosity, so in a flux-limited sample, they're maybe 1 in 100. But it's difficult to weed out all the things you don't care about and find the ones that you do care about at this phase. Because at this phase, they look a lot like a type 1a supernova. They're maybe a little bit brighter, a little bit fainter than a type 1a supernova. And so it's going to be hard to tell them apart. So you need a follow-up strategy and a discovery strategy to address this. So I've been looking at this in a couple different ways. One is we've designed and implemented a spectroscope to actually start classifying more of these events earlier. And another thing is, as I'm looking into now, more than looking into, we're actually starting now a search to find these objects at earlier phases. So the key here is that since they're so rare, you want to cover a large volume of the universe. You also, since that initial peak is relatively faint, you want to find the ones that are closest by, because those are the ones that are going to be bright enough for you to see. So you want to find something that's very rare. You want it to be in the nearby universe. So that means you have to cover a large volume of the universe. That means you have to cover a large angle of the universe, right? We can't just do a pencil beam survey for these. So we need a very wide field instrument to be discovering these events. And there are some surveys coming online, like the Zwicky Transient facility that will start improving this. But since I'm the director of an observatory, I have my own plans here. So let me actually first start by giving you some scale for this. So you know we have this hypersuprime cam, which is an amazing instrument, and it's a very wide field instrument, especially for an 8-meter class telescope. The field of view for the hypersuprime cam is several moon diameters across, about 3 moon diameters across. To give you some perspective on what that is, if you stick out your hand and put your thumb up, and you look at your thumbnail, that's a little larger, actually, than the field of view of hypersuprime cam, right? So if you actually do this, and you think about all the stuff you're not looking at, you're missing a lot of universe, especially nearby universe. So what we need is something that doesn't have a little pencil beam survey. We need something that has a beam more like this. So we want to get everything nearby. And ideally, you want to get it all the time. And we can do that. We have the technology. It's actually fairly straightforward. Here it is. This is an instrument called EveryScope. And what this is this is a hemisphere with effectively a bunch of telephoto lenses plugged into it. So these have a 6 centimeter aperture, so a far cry from Subaru in some respects. But we have 24 cameras on this, and they cover this much of the sky. And they do it all the time. So they take an exposure of 8,000 square degrees every 2 minutes. All right? So it's a pretty modest instrument. We're not going very deep, obviously, because our aperture is so small. We're going much, much more shallow than you would with a Subaru. But our étendue is actually pretty comparable. Étendue, by the way, is you take the aperture and you multiply that by the field of view of the instrument. It's kind of a measure of your survey speed. The survey speed for this instrument is actually similar to HyperSuPrimeCam. It's just we're looking at the very nearby universe. HyperSuPrimeCam is looking at the very distant universe. Okay. It's a big project for us. It's very modest in size. These are actual human beings here climbing on it to give you scale. It's led by Nick Law at the University of North Carolina. This actually exists. This has been installed for 2 years now and operating in CTIO in Chile. So it's been up and running. There's one exposure. That's one picture. This is not a mosaic of many pictures. This is what it takes every 2 minutes, exposure like this. This is 100 degrees across. We do have a lot of pixels here, and that's a zoomed out view. And we have this one in CTIO already. We're going to put one here in Mount Laguna Observatory. So we'll have two, one in each hemisphere. It's being built right now. And what we can do with this is we can actually, since we're getting everything all the time, we don't have to do a targeted survey. We can, whenever your transient goes off, we got it. So I heard Nao Suzuki saying before that we can move our telescopes over there in 3 minutes and start taking data. With every scope, we were there 3 minutes before. Right? So we can start taking data before it gets there. And I was just going to show you this very briefly. If you look very closely right there, you'll see a supernova. This is a supernova that popped off. And we didn't know about this at the time, but that's actually a supernova a few hours after it exploded. And that's a clearer view one day after. So we have this ability to catch these fairly low luminosity nearby faint transients. We can do that for the superluminous supernova. This is a normal shock breakout supernova. Is there any other fast transients you guys can think of that we can discover with this? I'll tell you what. I'll give you 30 seconds to figure it out. I'll set a timer here for you. When it gets to the end and it chirps, that's your clue. You see where we're going with this? Wait for it. The last second is the best. So just to cut the chase, unfortunately, we didn't get this one because this one went off during the daylight. It had the goal to do that, so we weren't observing when it went off. But if we did have an event like this go off, apparently, if it was similar to this, it would be bright enough for us to detect with that instrument. So we wouldn't need any trigger. We'd just be on the sky taking data. And we can not only say, here it is, but we can say it wasn't there 2 minutes ago. And that would be very crucial for getting fast follow-up of this. So I think that's it. Thanks.
Thank you very much.